Okay, so you've probably, kind of reviewing atomic structure a bit, you've probably seen this very simplified model of the atom back whenever you started talking about atomic structure in Chem. Now, this is what is known as the Bohr model, right? And what you're looking at here is you've got the nucleus in the center, right? That's representing the black dot, represents the nucleus. And then you've got the n equals 1, 2, 3, 4, almost like it's like a solar system type thing. Those n equals 1, 2, 3, 4 are what are known as the principal electronic shells. And according to the Bohr model, the atom was a lot like a solar system type thing, where instead of a sun in the center, you have your nucleus, and then kind of surrounding in these principal electronic shells, the nucleus, you had your electrons. And the electrons could jump between the different principal electronic shells with given sufficient energy. Okay. The slide over here, what's kind of represented over there is almost like if you took like an ice core of the Bohr model here. So imagine if we were to kind of just take a box and do that. That's what over here on the right side of the slide represents, where down here you would have the nucleus, and then those principal electronic shells are moving further and further away from the nucleus. Okay. Now, what's important to note here is as the n number increases, right, if you go from n to 1 to 2 to 3 to 4, we're getting farther and farther and farther away from the nucleus. So those electrons that are higher in number are further from the nucleus and thus less tightly held. They're not as, remember, you have the positive charge of the nucleus that is serving to attract the negative charge of the electron. So the farther you get from the nucleus, the less of that attractive force is felt. So these electrons out here are less tightly held than the electrons down here. That's going to play a big role in reactivity. Now, it turns out that the Bohr model worked well for hydrogen and not so well for anything beyond that. It got a little bit more complicated. And that's because within each of those principal electronic shells, we have these kind of further subdivisions or regions of electron density that we call the orbitals. And so you might remember from Gen Chem, you probably learned that you had, in terms of the atomic orbitals, you had the S, the P, the D, and the F orbitals. I've got more good news for you. We don't care about the D and the F. In organic chemistry, we're not really interested in metals. So we don't need the D orbitals because that's all the transition metals. We don't need the F orbitals because that's all the lanthanide and the actinides. Basically, all we're going to care about for this class are about the mainly the first 2 rows of the periodic table. Sometimes we'll dip into the third, but that's it. So making things simpler and simpler all the time. But the S atomic orbital, you'll notice it's kind of it's basically spherically symmetrical. And when I talk about an orbital, remember all we're referring to here is a region of electron density. Saying it another way, it's kind of the likelihood of finding an electron. And you can see a little bit hard to see because of the grayscale, but what it's trying to show you is you have, by the way, the nucleus would be kind of in the center of that. So there's more likelihood of finding an electron closer to the nucleus. That's why it's a little darker kind of towards the center. But the thing about the s orbital is that it is spherically symmetrical. So there's only one type of s orbital, right? Because you can't really, because it is a sphere, a ball, if you will, I can't really take it and rotate it 90 degrees and get something else. Right? If you take a sphere and rotate it 90 degrees, it's still the same sphere. Again, it's spherically symmetrical. So there is always only ever one s orbital per electronic shell. So you can have a 1s, you can have a 2s, a 3s, etc. And the only difference from those is, again, the distance from the nucleus. The 1s is closest to the nucleus, followed by the 2s, followed by the 3s, etc. Okay. Then we get the p orbitals, the p atomic orbitals. And these are kind of dumbbell shaped, right? And again, the nucleus is kind of in the middle. You'll notice that these are not symmetric, right? They have directionality associated with them. So you have the P that lies along the x-axis. And then if you rotated that 90 degrees, you get a P that's on the y-axis. And if you rotate that 90 degrees, you get a P along the z-axis. Okay. So we actually have 3 separate P orbitals as a result. And you can see that this is kind of illustrating the 3 different P orbitals all overlapping on one another. Okay. They are orthogonal to each other, 90 degrees apart. Now, the other thing to note is that while electron density was highest at the nucleus for the S, we have a region here that we call a node, or nodal plane. A node is a region where there's no probability of finding an electron. Okay, so between the lobes of any of these 3 p orbitals, there is a node where there is 0 chance of finding an electron. But these are the orbitals that we are going to be concerned with for organic chemistry. The S's and the P's, you can completely disregard the D's and the F's for this class. So kind of maybe a more accurate picture of atomic structure would look like this. So this includes both the principal electronic shells, the 1, 2, 3, 4, and it also includes the orbitals within each one. Okay. So you can see at the first principal electronic shell, you only have access to the s orbital. Okay. You don't get access to the p orbitals until you move into the second principal electronic. So there you get a 2s and a 2p. All of the principal electronic shells have an S. Move up to the third electronic shell, you get the S, P, and the D's. But again, not so important for us. And like I said earlier, we're really going to be focused on that region of atomic structure. So this allows us to kind of diagram would allow us to do pretty easily that what you learned back in Gen Chem, that electronic configurations, right? So for example, if pick an atom, if you wanted to figure out what the electrons look like within well, the first thing we need to do is figure out how many electrons do we have to find a home for? So, find that on the periodic table. Right? Oxygen has an atomic number of 7. Right? Oh, 8, sorry. Atomic number 8. So that means it has 8 protons, but because all atoms are neutral, it also means it has 8 electrons. So basically, we've got to fill this in with 8 electrons. But you'll also recall back from Chem, you cannot just arbitrarily fill them in. Right? I cannot just randomly start putting electrons in those. They have to be filled in accordance with 3 rules. The first of which is what we call the Aufbau principle. It's a German word meaning to build up, and that's basically what it is. The Aufbau principle says that you have to fill the electrons in from low energy to high. So basically, you could not start filling in our 8 electrons of oxygen. You could not start that at 2p because you have lower lying orbitals. So basically, we're always going to start at 1s, and then you go to 2s, and then 2p, and then 3s, etc. You go in order of energy. Now, the second guideline for electron configurations is what's known as the Pauli exclusion principle. And this says that you can only pair electrons in an orbital if they have opposite spin. Okay, so if you think about it, if you consider an electron as a particle, these guys are spinning. And so you can only put electrons together within an orbital if they have opposite spin. One is kind of clockwise, the other would have to be counterclockwise, essentially. The way we typically represent that is with arrows. That would be one spin state. That would be the opposite spin state. So that's how we kind of represent this quantum number of spin. And then finally, the third guiding principle for electron configuration is what's known as Hund's rule. And Hund's rule talks about when you have orbitals at the same energy. So, for instance, the p orbitals. Anytime you have p orbitals, you'll notice they occur in threes because you have a px, a py, and a pz, as we talked about. And all 3 of those are of exactly the same energy, or what we call degenerate orbitals. Meaning they're at the same energy level. And what Hund's rule says is that when you have degenerate orbitals, you're not going to pair electrons until you have to. Right? Meaning that if you, well, let's start with oxygen. So we said oxygen has 8 electrons. So according to Aufbau, we'll start at the 1s. And we can put 2 electrons per orbital as long as they have opposite spin. So there's 2. We have 6 more to place. So we'll go to the next highest. That's 4. Now we've got to put the remaining 4 electrons in the orbitals. What Hund's rule says is that you're going to place them singly first, and then pair up if you have to. Again, what you're going to find is organic chemistry, again, is obsessive about electrons. One of the most fundamental things you need to remember about electrons is they have the same charge, and like charges repel. So basically, electrons don't want to be close to each other. Anything that leads to electrons being close to each other is going to mean a higher energy state. And so if those electrons can be away from each other, meaning in different orbitals, that is what they're going to prefer. So when we go to start putting these electrons in these degenerate orbitals, they're going to go in singly first. What does that give you? 4, 2, 4, 7. So we got 1 final electron, and so it can go in really any of them. So that would be the electron configuration of oxygen. And the way we would write that out, so you don't generally have a big schematic like this. The way we would represent that is we would say 1s2, right? Because the superscript here represents how many electrons are in that particular orbital. So we have 2 electrons in the 1s. Then we have 2s2, 2 electrons in the 2s. And then we have 4 electrons in the 2p. So we would write 2p4. And that would very simply be the electron configuration for oxygen. Describe how the electrons are distributed within the atom. No, degenerate means they're of the same energy, right? Because all 3 of those p orbitals are at exactly the same energy level. That's why we call them degenerate. Okay, so let's go ahead and look at a couple examples. A couple other examples. Let's do nitrogen. Actually, let's skip nitrogen. Let's do some of these bigger ones. Nitrogen is pretty much the same as oxygen. Let's do chlorine and sulfur. So, total number of electrons of chlorine, periodic table tells us that, 17. Now, you could certainly do these configurations with that kind of schematic, but most people don't. Most people will use the periodic table because you'll remember that the rows represent the principal electronic shells. And then the various blocks represent the atomic orbitals. So that would be the S block, the P block, the D block, and the F block. But again, we don't ever care about the D and the F. We're going to be focused on the S's and the P's. So basically, if we're trying to figure out the configuration of that guy, chlorine, we can use the periodic table to guide us. So we've got 1s2, that accounts for hydrogen and helium. Then we go down to the second. 2s2, that accounts for lithium and beryllium. Then we jump over to the 2p's, and we're going to go 2p6. And that gets us to neon. And then we go down to the 3's, 3s2. And then where are we? 3, we want 1, 2, 3, 4, 3p5. And that gets us to where we are trying to get. Now, you'll also remember, because, I mean, doing electron configuration like this is fine. But it gets a little bit tedious. Like if I were to ask you, give me the electron configuration of polonium, that's a lot of work, right? Because you've got yeah, 84 electrons. That's kind of a lot to do if you're starting at 1s2. So what a lot of times people will do is instead of writing out this exhaustive list, is they'll use kind of a shorthand, what we call noble gas configuration. And the noble gas configuration is really, really easy. You just find the previous noble gas to where you're trying to get. In this case, if we're trying to do chlorine, the previous noble gas to chlorine would be neon. So I'm going to put neon in brackets. And what that's saying is that I've got all of the electrons that hit me here. And then we put in the remainder, which will just be 3s2, 3p5. So that would be the noble gas shorthand. The other thing that this does for us, it's kind of nice, this shorthand, is it distinguishes between the inner or core electrons from the valence electrons. When I say valence electrons, I mean the outermost electrons. And that's an important distinction, because those valence electrons are really what we care about. They are the ones that are on the outside of the atom that are able to actually do things. Right? Go attack something. Like be picked off by something. I can't get to the inner or core electrons because they're covered up by the outermost shell. It's almost like kind of an onion, layers of an onion. You can't get to the innermost layer of the onion because you've got all those intervening shells. Same thing is true with the electrons. So those outermost electrons are the ones responsible for reactivity, and thus they're the ones we care about. And so that's why this noble gas configuration is kind of nice, because it distinguishes between all of the inner or core electrons that don't make a difference to us and the valence electrons that are responsible for reactivity. So if I were to ask you how many valence electrons does chlorine have, all you have to do, add up the superscripts. In the outermost shell, which for the case of chlorine is the third principal electronic shell, there are 2 plus 5. There are 7 electrons in the outermost shell, or said another way, we have 7 valence electrons. And then the other thing that I want to kind of remind you about is the Lewis dot structure. The Lewis dot structure is just another way of kind of representing an atom with its valence electrons. So the way we represent Lewis dots is we'll put the atomic symbol for chlorine Cl, and that atomic symbol represents the nucleus and the inner or core electrons. And then we use dots to represent the valence. We already said we have 7 valence electrons, which means I need 7 dots around the chlorine. And we typically kind of draw them in one at a time, kind of like when you're doing the, almost like a Hund's rule type thing. We're only going to start pairing them when we need to. So there's 4, 5, 6, 7. That would be the Lewis dot structure of chlorine. Questions there? Mm-hmm. Not really. Yeah. All right, let's do one. Why don't you try sulfur on your own? So go ahead and do the noble gas configuration. Tell me the number of valence electrons, and then draw the Lewis dot structure. Oh, yeah. Where did I put it? Oh, there we go. All right, so sulfur, 16 electrons, we've got to find a home for. It's in the third principal electronic shell, so that means the previous noble gas is also going to be neon. So we've got 3s2, that takes care of sodium and magnesium, and then in the P, we go to 3p, 1, 2, 3, 4. That's a 3p4. So how many valence electrons do we have in sulfur then? 6 valence electrons. And so we go in and we start filling the dots in to represent the valence electrons. We've got 6 valence electrons, which means we need 6 dots. So that would be my Lewis dot structure of sulfur. Now, one other thing I want to kind of highlight here, atoms are always going to form the number of bonds, same number of bonds, as they have unpaired electrons. So you can look at the Lewis dot structure of sulfur. You see it has 2 unpaired electrons. Sulfur is always going to make 2 bonds. What about chlorine? Chlorine has only 1 unpaired electron. It will always make 1 bond. Okay? All right, questions there? Okay, so let's go ahead and look at, we talked about this a little bit earlier in lab, but just to kind of remind you, when it comes to making bonds, as we start to use these atoms to form compounds, we generally will broadly classify them into 2 bond types, the ionic bond and the covalent bond. And as we discussed, that largely depends on the electronegativities of the things you're combining. If there's a very, very large difference in electronegativity, say between a metal and a non-metal, and that magic number there, that's greater than 1.8 WN, that will be classified as an ionic bond. Basically where, so that would be sodium with its 1 valence electron, and I'm going to combine it with chlorine with its 7 valence electrons. In an ionic bond, the metal is said to give its valence electrons to the non-metal. And what that does is, because the sodium is losing an electron, it renders it positive. The chlorine is gaining an electron, making it negative, and that is an attractive force. That is the bond that holds those 2 things together. But again, the goal with bonding is always the same. The reason atoms form bonds is so they can achieve their octet. This satisfies the octet of both of those atoms. Alternatively, we can have atoms sharing electrons. We saw this as well. We looked at the example of a molecule of chlorine. So they will share that pair of electrons, and by doing so, it gives each of them 8. And we typically don't represent a compound in that way. It would be much more common to represent it as Cl with a dash between. That dash represents the shared pair of electrons, the chemical bond. Okay. Questions there? Mm-hmm. Sorry. Oh. I would say 0.4. Yeah, but again, because that is the difference between carbon and hydrogen. Okay, what if I were to give you this one, CH2Cl2. So let's see if we can draw a Lewis structure of this compound. Now remember, carbon has 4 valence electrons. Hydrogens each have 1. And as we said, chlorine has 7. So could you arrange these 5 atoms together in order to get a neutral organic molecule? And what I'll call your attention to, just remind you of, is atoms are always going to make the same number of bonds as unpaired electrons. Hydrogens each have 1 unpaired electron. Hydrogen always makes 1 bond. Same thing is true with the chlorines. Chlorines both have 1 unpaired electron. Chlorines will always make 1 bond. Carbon has 4 unpaired electrons. It will always make 4 bonds. So that's how we'll put them together. Pair those 2, pair those 2, pair those 2, pair those 2. And the way we would write that is like that. And if you want to be a stickler, you can draw in your lone pairs. Questions here? All right. This is just something to kind of keep in mind, and it kind of goes to what I just mentioned about atoms forming the same number of bonds as unpaired electrons they have. These are just some general motifs to keep in mind, especially as you start drawing your organic molecule. You start drawing a molecule and you get to a oxygen and you've got 4 bonds on your oxygen, that's not right. Okay. Carbons always make 4, hydrogen's always 1, oxygen's always 2, nitrogen always 3, halogen's always 1. Okay. Now, you can have variations of this. I mean, I said a carbon always has 4 bonds. I've shown an example here, 4 single bonds. But that's not the only possibility. All I said was that a carbon has to have 4 bonds. So you could have something like that, 2 singles and a double. I could have 2 doubles. I could have triple and a single. Right? Any permutation will work. You just need your carbons to always have 4 bonds. Okay, same thing is true with all the others. You know, I have oxygen shown down here with 2 single bonds, but I could just easily put something like this. Instead of 2 singles, it has a double bond. Still 2 bonds. Okay. But this, again, this is something worth learning, memorizing, whatever. because that will hopefully help you avoid making mistakes when you start writing out molecules. Let's do some practice with that. You can draw out the Lewis structure of something like this. By the way, this is what we refer to as a condensed structural formula. So we got kind of all of the atoms in the right order. We just haven't drawn in the explicit bonds. Go ahead and translate that. Take this condensed structural formula and turn it into a real Lewis structure. Okay, so the simplest thing to do when you're trying to figure these out is just draw them out exactly as they're written. So I've drawn out my CH3, that accounts for that. Connected to the CH2, that accounts for that. Next in line, I'm going to put in my oxygen. Connected to a CH2. Now we do have to consider lone pairs. How many lone pairs should oxygen have if it's neutral? Always 2. What about nitrogen? How many lone pairs does nitrogen have if it's neutral? 1. So that's kind of what I'm kind of feeling right now. We could go through and just verify that everything has its octet. That carbon has 4 bonds, good. Carbon has 4 bonds, good. Oxygen has 2 bonds and 2 lone pairs, good. 4 bonds. Nitrogen has 3 bonds and 1 lone pair. That's good. So that one was pretty straightforward. What if I ask you about that? This one introduces kind of a novel thing. This is the parentheses. What the parentheses indicate is that, say you've got CH3 bracket 2. That means you have 2 of these groups that are on that carbon. However many groups are in parentheses are present on the previous atom. So what this is going to look like, got my CH3 that I'm going to start with. And that's connected to a CH. And that's connected to a C. And on that C, I've got 2 CH3 groups. There's 1. There's 2. So I just drew that in exactly as it's represented above. And are we happy? Something missing. Yeah, have a look here. This carbon does not have its octet. For that matter, neither does this. So how could we fix that? What would make each of those electron deficient carbons happy? Yeah, put a double bond in between them. Now everything's satisfied. Questions there? So that's one thing you can, if you're working through these and you write a structure and you notice that not everything has its octet, that is a trick you can use. Put in double bonds, put in triple bonds. That'll sometimes fix it. We'll look at this last one with you. This illustrates another little trick you sometimes have to do. So again, I'm going to go ahead and start this exactly the way we did the previous ones, just kind of start writing them out exactly in order. Got a little bit lazy over here. So you can see I've got the So instead of drawing all of those bonds, those CH bonds explicitly, I just kind of put CH2, CH3, CH2, CH3, CH2, CH3. That is the three different CH2, CH3 groups that are on that carbon. So are we satisfied with this? That's the problem. Over here is fine. This carbon has 4 bonds and all of the CH2, CH3 groups. Those are all good. This carbon over here is good. But everything in the middle is not good. So anybody see these two carbons are obviously not happy? Anything we can do here? Yeah, I'm kind of leaning towards a triple bond there. What is that going to do for us? Ooh, God. Okay, so that fixes those carbons. That's good. Now these guys are happy. Are we done? I could put a lone pair there. Are we happy now? That carbon. What do we do with that? What we've done previously is put in double or triple bonds. Could I put a double bond in between the first two carbons? No, because then that carbon would have too many electrons. All right, well, what about a double bond between the carbon and the nitrogen? So that we'll erase the lone pairs and put a double bond, but then think about what that would do. That would give the nitrogen 4 bonds, 0 lone pairs. It would no longer be a neutral, right? We can't really move hydrogens because that is the structure. So you can't just arbitrarily move a hydrogen because it's not convenient for it. So this is the other trick. In addition to using double and triple bonds to fix valences, sometimes you have to pull something out of the parent chain. when I say pull something up, what I mean by that is a heteroatom. It's commonly known as nitrogens with oxygens, sulfurs, but out of the main chain. So what I mean by that is I'm going to erase the nitrogen from the middle. Bring these a little bit closer so it looks not quite so weird. So I've got a place that NH group I just erased, but it's still obviously something we have to deal with. So you see how I know it's bonded to that previous carbon. So I can put it on that carbon. Like so. Is that right? Still not right. That carbon still does not have its octet. But what do we do there? Yeah, put a double. I think that fixes it. Huh? Yeah. You don't usually do. Yeah, no, because it's, I mean, yeah, I mean, I guess you could, but you don't normally see that. You don't normally see the parentheses unless you have multiples coming off the same carbon.
So when can you do that then?
Anytime.
Oh.
As long as it doesn't violate an octet. So I guess the way I would approach these is kind of the way that I introduce them. You know, start just drawing everything out in a line. A lot of times that works, like here. If you notice some issues, start trying to fix valences with multiple bonds. Put in a double bond, put in a triple bond, see if that works. If that still doesn't work, that's when you want to start thinking about pulling heteroatoms out. And again, that is usually just going to be reserved for nitrogens and oxygens. Questions there? Okay, so it's kind of a related topic of what we've been talking about, going between these different structural formulas. In organic chemistry, what you're going to find is we almost never represent molecules as a molecular formula. You know, back in Gen Chem, you probably saw a lot of that where you represented compounds simply by their molecular formula. Na2CO3, Na2CO3, for instance, sodium carbonate. Li2SO4, lithium sulfate. So it is quite common to represent compounds by their molecular formula in Gen Chem. We almost never do that in OChem. And the reason being, so let's think about that compound, 3-methylbutan-2-ol. Molecular formula C5H12O. That tells me almost nothing about that compound. If I just saw C5H12O, put that together in a lot of different ways. Make it an alcohol. Make it an ether. You might be able to make it. There's a bunch of different ways to put that together. There's a bunch of multiple different alcohols. There's multiple different types of ethers. There's probably about 5 different compounds that I could draw that would be C5H12O. So it's really kind of ambiguous. So to avoid that ambiguity, instead of representing these compounds at their basic molecular formula, we use structural formulas. We've already been looking at that a little bit. You know, I can draw the full-on Lewis dot structure like this. That would be the full-on Lewis dot structure. And yeah, that shows exactly how the atoms are connected in this particular alcohol. But you can probably see that this would begin to get a little bit tedious. If you had to represent all of your molecules in this fully explicit, drawn out view, it gets tedious. It takes up a lot of space. And so we don't generally do this either. What we're going to do is kind of try to find some sort of a shorthand way of doing this. And you can do a condensed structural formula. That's kind of what we are working with in the previous problems. So that would be the condensed structure. Yeah, kind of what I showed you with those three examples that we looked at previously. But sometimes it's nice to have a little bit more information than that. You know, I mean, you could certainly figure out, I'm sure if I gave you that, you could come up with that. Take a little bit. Probably take you a couple minutes, but you could figure it out. So a lot of times what you will do is give you a little bit more information so you don't have to spend so much time translating. So this partially condensed, what I'm going to do is pull out the branch things. So that's kind of like, kind of shows you more explicitly how things are connected. You don't have to do quite as much thinking. Oh, dang it. I'm out of time. Okay, so we will pick it up from there. What we're going to start with on Thursday is the most important of the representations, the so-called fine angle form. That is the way that we are going to be representing molecules from here on out. So we're going to get a lot of practice interpreting those. All right. So I will see you back here on Thursday. Hope y'all have a good evening.